Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks section 13.4 titled Walks, Trails, Circuits, Paths, and Cycles. Now, hopefully you recall all the junk from directed graphs way back when. You have actually seen these words defined before in a directed graph. And the definitions do not change for these undirected graphs that we are now looking at. Let's just get into it and you'll see what I mean. Alright, so suppose a graph represents a road network with the vertices corresponding to intersections and the edges to roads that connect those intersections. A natural way to use such a graph would be to plan routes from one point to another that pass through a series of intersections. In the language of graphs, a walk is a way to travel from one vertex to another by a series of hops along undirected edges of the graph. So they define a walk here, right? A walk from vertex V0 to say vertex VL in an undirected graph G is a sequence of alternating vertices and edges. Starts and ends with a vertex, right? So you say you start at vertex V0, then you travel along this edge to vertex V1, then you travel along this edge to vertex V2, and so on, and you finally end up at vertex V sub L. The vertices just before and after each edge are the two endpoints of that edge. Right? You see this vertex V0 and V1 are the endpoints of edge V0, V1 here, and so on. Now, since the edges in a walk are completely determined by the vertices you travel to, a walk can be condensed to just write the vertices that you travel to. Right? So I'll look at walks mostly like this. The sequence of vertices is a walk if the edge from vi minus 1 to vi is actually an edge you can walk on. Right? You only have a valid walk if you can actually get from one vertex to the next on an edge. Alright, the length of a walk is L, right? The number of edges. So really, if you look at it, if you write out a walk using only the vertices, the length of the walk will be the number of vertices minus 1. As you see here, there are L plus 1, 0 to L. There are L plus 1 vertices, but that would mean you traveled along L edges. So it's the number of vertices minus 1. That's the length of a walk, how many edges you traveled on. An open walk is a walk in which the first and last vertices are not the same, so you don't end where you started from. And a closed walk is a walk in which the first and last vertices are the same, right? So where you ended where you started. All right. Now, they're just going over here the difference between, remember we saw directed graphs before where there were arrows and you could only go in one direction. So from X to Y here. Right? Undirected graph, you can go in both ways. Right? You can go V to W, W to V. It's the same edge. All right, so that's all they're saying in this. All right, so look at this example. I will play the animation. So here's this graph, an undirected graph, simple graph. So there's, I'm starting a walk at vertex A, and I travel along this edge to vertex E. So I got the walk A comma E so far. And then I'm going from E to B. So I label B, and then B. Now, B to D, can't do it. All right, there is no edge directly from B to D. So this is an invalid walk. Not a walk in this graph. Alright, so then they change it up a bit, like, oops, I made an error. But now I can go from B to C, sure, there's an edge. And there, this walk from A to E to B to C has a length of 3, right? There were 3 edges used in this walk. And notice again there are 4 vertices written here, right? 4 minus 1 is 3, right? So the number of vertices minus 1 is how many edges you've used. And it's an open walk, right? Notice I ended in a place that I didn't start from, right? In a different place that I started from. The last vertex is not the same as the first vertex. All right, well, then they do another one. Here, starting at A again. Now, if you don't do anything, right, a single vertex is a walk of length 0, right? You didn't travel along any edges. So if you just close it off with one vertex in there, 1 minus 1 is 0. This is a walk of length 0. And starting at A again, here's to E, to C, to B, to E again, and then back to A, which you can do, it's still an edge. There are these 5 edges, right? There are 6 vertices listed. So 5 edges, the walk has a length of 5. And it is a closed walk because the beginning edge and the beginning vertex and and ending vertex are the same. Right? So just some examples on this picture here, going over walk, the length of a walk, how to list it, and is it open or closed. All right. So for example here, which of the following sequences of vertices is not a walk in the graph? So I'll read this out loud and follow on my cursor on the graph up here. So from A to B, yeah, I can do that. B to E, I can do that. E to F, sure. F to E, yeah, I just go right back. So that's a valid walk. A to B, B to E, E to B, sure. B to C, yeah. There's edges between all those. All right. So it must be the third one. Let's see. A to B, B to C, C to E. There's no edge. So that one's not a valid walk in this graph. What would be the length of this walk? Well, let's see. There are 6 vertices, so it'd be of length 5. Right? You'd be crossing 5 edges. This has 3 vertices, so it would be length 2. Very simple. And which of the following walks is a closed walk? So this one, you begin at A, you end at B, that's open. This one, the third one, you begin at A and end at F, that would also be open. This second one, you begin at B, you end at B, that's closed. Okay. So again, very similar to the section when we had directed graphs and saw these same definitions: walk, open walk, closed walk, the length of a walk, all that same stuff. But now you don't have arrows, certain directions to follow. You can go back and forth. This is undirected. Okay. And then all these definitions also came up before, right? These are special kinds of walks: trails, paths, circuits, and cycles. Now I set them in that order. They have a different order because trails and paths are examples of open walks, special open walks. And circuits and cycles are examples of special closed walks. And it's easy, I find it easy to remember these. Circuit and cycle both begin with C, and so does the word closed. Right? And then trails and paths, don't begin with C, so they're not closed. They're examples of open walks. All right, so what's special about them? A trail is an open walk, right? So you begin and end at different vertices, in which no edge occurs more than once. Right? So a trail is an open walk where you don't go across the same edge twice. Right? Every edge you use it once, and then you can't go back. You can't use it again. Right? Even in reverse, right? There's no direction here. A path is a special kind of trail. So a path is a trail in which no vertex occurs more than once. So you can't use the same edge more than once, and you can't land on the same vertex more than once. That's a path. All right, now a circuit. A circuit is a closed walk in which there's no edge more than once, right? You can't go across the same edge more than once. But you begin and end at the same place, right? It's a closed walk. A cycle is a circuit, so you can't use the same edge more than once, and you can't use the same vertex more than once, except for the beginning and the end, right? And it's got to have length more than one too. You can't just do like, oh, I'm going to stand here and not move. That's not a cycle. So it's a circuit of length at least one in which no vertex occurs more than once, right, except for the first and last one, because it's a closed walk, right? You start and end at the same vertex, but no vertex repeats in between. And no edge, right? It's also a circuit. So they give you some examples here. Let's just go into a picture. All right, I'll play this animation. So there's another undirected graph. Now here they're starting at A, C, go to E, go to B, go to C. And if you stop, that's an open walk, and every edge was only used once, right? And every vertex was only used once. So it is a trail, but it is also a path, right? Every path is a trail, but not every trail is a path. Right? It's a trail because no edge is used more than once, and it's also a path because no vertex was hit more than once. All right. Next example. Again, start in A, go to E, go to C, go to B, go to E. All right, now this is also an open walk. All right, it's open because I started at this, A, and I ended at E. It's a trail, right, because I didn't use any edges more than once, but it's not a path, right? It's a trail because I used every edge only once. It's not a path because the vertex E was hit twice. You repeated a vertex in this open walk. So it's a trail, but not a path. Next example. Starting at B this time, go to C, go to E, and go right back to B. Well, look at this. This is a closed walk now, right? It's a B to B. It's a closed walk, and every edge was used once, then go back over any edges. So it is a circuit, right? It's a circuit, but a circuit could also be a cycle. All right, let's see. Well, again, other than the first vertex and the last vertex, are any other vertices hit more than once? Well, C wasn't hit more than once, E wasn't hit more than once, so this is also called a cycle. All right, so it's a circuit because no edge was used more than once, and it's a closed walk. And it's a cycle because other than the beginning and the end, none of the vertices were hit more than once. They would also call this a 3 cycle because it's a cycle of length 3. Right? There are 3 edges here. Another example. All right, so this time they're starting at E, go to B, go to C, go to E again, go to F, go to A, and then back to E, and then stop. Now, that whole walk, E to B to C to E to F to A to E, it's closed because you begin at E, you end at E. It's a closed walk. Every edge was walked on only once. So it is a circuit. because every edge was only walked on once, only used once. But it is not a cycle, because vertex E is repeated in the middle of the walk. Right. So it's a circuit, but not a cycle. All right. And then there was one back here. Right. You see this one where A to E to C to B to E to A. This one is a closed walk, but that's it. See, there's an edge used twice, A, E, E, A, right? So it's not a circuit. And the vertex E is repeated, right? You got E there, right? So it's not a cycle. I mean, if it's not a circuit, it can't be a cycle, right? If it's not a circuit, it can't be a cycle. Same thing for open walks, right? If it's not a trail, it can't be a path, right? Based on the definitions. Okay. All right, so let's look at this one. So similar picture to earlier, same picture. Now, which of the following sequence of vertices is a circuit? All right, so remember this is a closed walk that doesn't repeat any edges. So that's not closed, but these three are closed. You see how this repeat is A, E, E, A? A, E, E, A? That means there's a repeated edge. This one, closed. Yeah, it doesn't repeat any edges. This one's closed. Now let's see if any of them are a valid walk though. Like, we got A to E to F to G to A. Yeah, that would be a circuit. B to G. Yeah, see, here's the problem here. B to G. There is no B to G, so this one's not even a walk. So it's this one. Which of the following sequence of vertices is a trail? Remember, a trail is an open walk, so it can't be the second one. That's closed. And a trail is an open walk where, again, no edges are repeated. So you won't see the same vertices in different orders, back to back. So like this one here, you got A, B, and then you got B, E, E, B. That's the same edge twice, B, E, and E, B. So this is not a trail. It's got to be this third one. Is the following walk a path? Remember, a path is a trail with no repeated vertices. Well, this repeats vertex E. So it's not a path. And is the following closed walk a cycle? So remember, a cycle is a circuit. And it's a closed walk with no repeating edges. And, in between the first and the last, you got no repeat, you don't repeat any vertices. So I'm not going to see A again, B, I see B here, I'm not going to see B again, I'm not going to see C again, F again, E again. This looks like a cycle, right? I have, if I walk it out here, and you got A to B, B to C, C to F, F to E, and E to A, and you get this like, 5 cycle here. Yes, this is definitely a cycle. No, it's a circuit, right? No edge occurs twice, more than once, and no vertex except the beginning and the end. Repeat more than once. All right, so just a lot of definitions. Same definitions you saw for directed graphs. So I'm hoping this section is relatively simple. All right, so you have your additional exercises. Some of these are assigned, some might not be. Even if they're not assigned, I would still suggest you look at all of them, work on all of them, just to get more exposure, more practice. And you also have the solutions you can look at. Right? Just don't look at the solutions until you've tried them first. Try to work them out on your own first, and then look at the solutions, see how you did. You're not going to learn anything if you're just looking at the solutions and not working, not trying. Alright, and I hope this video is a decent guide through this section. Obviously, if you have any questions, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.